what we're going today is try to review a bit of what we discussed for the past few weeks, and then add a bit more of the derivation, meaning we want to convince ourselves that our equations, or the equations that we are using, basically comes from first principles. And of course, we introduce the physics behind these equations as well. Now, from this figure, you will now see the infinitesimal element that is subjected to a 3D state of stress. 3D state of stress, meaning you have all the necessary normal stresses, sigma 1, sigma 2, and sigma 3, and the shear stresses. So here you will have so-called 3 normal stresses and 6 shear stresses. Of course, we can, from this one, we will be able to, from your Hooke's law as well, we will be able to determine your equation of strains, normal strains, that is. So as you can see here, it's also possible to analyze this one in a 2D stress state of stress. We will be able to simplify this one here, but we have to have some assumptions. Before you can even transform or simplify this analysis to a 2D state of stress, we need to have some assumptions, which we will be discussing later. So what are these assumptions? To be able to simplify a 3D state of stress to a 2D state of stress. So there will be assumptions to that, and we have 2 assumptions, and we will be able to discuss that later. So here you go, you have 9 components of stress, 3 normal, 6 shear. Of course, try to remember that this first subscript here refers to the direction of the normal, or to that phase that this stress is acting upon. Now, you also have sigma 1, 2, sigma 1, 3. So as you can see, this stress here acts on this phase perpendicular to x1, that's why it's 1. And then its direction, second subscript, refers to the direction of stress 3 in the direction of x3. So instead of using x, y, z, in this course we're going to use x1, x2, or x3, or simply 1, 2, 3. So don't be confused with that. So here you go again. We will be deriving this one here just to convince you, meaning that if this one now is symmetric, then instead of 6 independent or 9 independent components, we will have 6 independent components. So 9, why? Because 1, 2, 3 normal, and 1, 2, 3, 4, 5, 6 shear stresses. But because of symmetry, this is equal to that, this is equal to that, and this will be equal to that. So we have now here 3 normal and 3 shear stresses because of symmetry. We will be deriving this one later. So this is just your equation for strain. Of course, you can express this one as a, also you can express this one to be stress equal to a function of strain as well, not a problem. So here you go, this is your beautiful equation here. Again, remember, strain is equal to your compliance matrix multiplied by the stress. If you want to write this one the other way around, you have stress equal to your stiffness matrix multiplied by your strain. And of course, these are given by these values here. Remember that your stiffness matrix is the inverse of your compliance, and vice versa. Okay, this is your so-called equilibrium equation, which we will be deriving first. Before I derive it, I would like to discuss some of this information first. Surface tractions and body forces This one is the force distributed to a surface of a body. Normally, this one is equal to a stress multiplied by a normal. So again, we were able to discuss last time that our state of stress, wherein we have normal and shear, we can rotate this one, your element, that infinitesimal element, such that you will have normal stresses only and zero shear. And this will be called your principal stresses, sigma 1, sigma 2, and sigma 3. Of course, you can express that also in 2D. This, of course, we will derive this equation here, or we will not derive, but we will get this equation from first principles and then leading to this one. So here, if you solve for your principal stresses, you can simply take the determinant of this one equal to 0, and then you can come up with an equation, or you can simply use this equation here where I1, I2, and I3 are invariants, and of course this invariance can be solved using these equations. So there you can have now your principal stresses. We also have discussed hydrostatic stress and deviatoric stresses. Of course, hydrostatic stress will be that normal stress trying to compress your 3D element. So this one is equal to the average or the sum of your normal stresses divided by 3 in 3D space. And this one is simply the sum of your normal stresses divided by 2 in 2D space. And again, of course, you can solve your deviatoric stresses using this equation. Also, from this one, you will also be able to solve your deviatoric stress invariance. So instead of I, for the deviatoric stress invariance, this is a new term that wasn't introduced last time. You can solve it using this equation. How will they be useful? We can study that in theory of plasticity later. So this is just an introduction. Right. So this is the first assumption to be able to simplify your 3D analysis to 2D. The first one will be the plane stress assumption. So what is the plane stress assumption? Now, this plane stress assumption assumes that one of the sides, or the thickness of one side, or the length of one side is much thinner than the other two. So, previously in a 3D space, so we have this one, wherein all the sides are so-called, or means all of the sides you must consider. They are all finite, wherein they are so-called measurable. Though measurable in terms of, or the difference between the length of each of the sides are not great. Great meaning more than 20, more than 30, and so on. They are comparable to begin with. So this is for 3D. Now, there are basically two assumptions wherein we can simplify the analysis to 2D. One is, of course, if let's try to have a look at this one here. So we have now this one here as your x1, x2, and x3. Now, let's have a look at this one here, wherein you have x1 and x2. Meaning that the dimension along x3 is very small as compared to the other two dimensions. So here, we can have here a plane stress assumption. So if we have a plane stress assumption, what happens? So the stress acting along that phase 3 will be equal to 0. So we're looking at sigma 3, 3, sigma 1, 3, sigma 2, 3 to be equal to 0. That is, if one side is much thinner than the other two sides. This is so-called the plane stress assumption. So that here, you will now be able to simplify the analysis. Instead of a 3 by 3 full house, we can simplify now this one to a 2 by 2. So take note here that these stresses are 0, but it doesn't mean that strain at strain 3, 3 will be equal to 0. It's just that this one is equal to 0. So as you can see here, we have now this independent stresses, so that your state of stress can be simply written as a 2 by 2 matrix. Again, the symmetry will be derived once I finish this discussing the other assumptions. So, there you go. For the plane stress assumption, this is now your equation. So these are your stresses, sigma 1, 1, sigma 2, 2, sigma 1, 2 equal to, this is now your stiffness matrix multiplied by your strain. Take note that strain 3, 3 is not equal to 0, but it can be computed since it is dependent on strain 1, 1 and strain 2, 2. So all of these are in the slides that you have. So as you can see, you have now this one to be reduced from a 6 by 6 matrix. It becomes now a 3 by 3 matrix. So that simply reduces your solution, plane stress assumption, meaning that one side is much thinner than the other. So the stresses on that side, so this one here, the stress acting on this phase here will be equal to 0. The second assumption is the plane strain assumption. So what does this plane strain assumption mean? So this plane strain assumption assumes that one side is much longer than the other two sides. So what does that mean? So let's try to recall first your concept of strain. So initially we have now this one here. This is, say for example, a beam or a bar, wherein you have this one to be your original length, and then we try to stretch that a bit, apply load, so that with this load, say F, you will have a small displacement delta. So you have that extension, so it will stretch. So how do you solve for your strain? Strain is equal to the displacement divided by the original length. So that's how you calculate your strain. Now let's have a look at a 3D element. So here we're now looking at one side to be much larger than the other. So then of course you have now here your x1, x2, x3. So one side is much larger than the other two sides. So what does that mean if you have this one to be very long and then you have a very small displacement? So let's try to calculate your strain. So you have E33 here, E22, normal, E11. Let's try to calculate your strain here. So we know that the strain here will be along this very long dimension here, along S3. Right? So meaning we're looking at this one to be much larger than the other side. So this one, say for example, displacement all over a length. But since this one is large, so what will happen to this value here?
Small.
So this one will be very small, but can be estimated to be 0. So meaning that if one side is much larger than the other, the strain along that axis will be approximately be equal to 0. So we assume that one strain is equal to 0. Of course, we're not saying that the stress is 0. We're just saying that the strain is 0. Yeah? So from there, any other strains associated with the axis 3 will be equal to 0. So again, we reduce the number of variables. So here you go, all the other strains along the 3 direction in our example is x3. So that of course we can have now your stresses. Like I said, sigma 33 is not 0, but we can take this one away because this one is a function of sigma 11 and sigma 22. So you can calculate that. So here you go for plane strain assumption. You have your non-zero stress, sigma 11, sigma 22, sigma 33, and sigma 12. But take note, this one is dependent on sigma 11 and sigma 22, so we just have 3. We only have 3 independent stresses. And of course, you have now your non-zero strain. So it can now be written in this manner here. So instead of, again, a 6x6 stiffness matrix, you're down to a 3x3 stiffness matrix, wherein sigma 33 is equal to this one here. So these are the type of loading that we will be able to study. But probably you have this one already in your mechanics of materials in your poly. So we have uniaxial or compression. So uniaxial, of course, it's either it's tensile or compression. You have biaxial, meaning the forces are acting in 2 directions. Biaxial. Triaxial, of course, say for example, you have axial force, you have another force here, transverse, and you have, say, torsion shear, wherein you have a full house. You have a full house matrix here. So if it's uniaxial, it's just 1D. Tension compression is just 1D. If it's biaxial, this one is 2D. And if it's triaxial, you have a full house 3x3 matrix for your state of stress. Now, we have done this one already when we were able to solve some simple example last time. So we have a beam bending. So if this beam is bending, and then you want to look at that infinitesimal element here, this will be subjected to 2 stresses. So it will be normal along here. So if you look at this one here, just take a look at this very small thing here. Yes, so we have now this one here, and we have this force there, or say a load. So if we're going to take an infinitesimal element here, so once this one bends, so if it bends there, so there will be a stretching. And then of course, because of that shear force there, there will be a shear there. So that you have this one to be sigma 1, 1, and this one is sigma 1, 2, sigma 1, 2. What about sigma 2, 2? It's 0. So that your state of stress is sigma 1, 1, sigma 1, 2, sigma 1, 2, and this one is sigma 2, 2, which is 0. So that is your state of stress. Of course, how do you solve for sigma 1, 1? That is your stress due to bending, which is my all over I. And how do you solve for your shear stress, sigma 1, 2? That is simply F all over A. So you have this in the slides. So that's the slide. Now, what about if it's pure torsion? So you're trying to twist this one, so it's all shear. No actual stresses or normal stresses acting on that element. So that, of course, your normal stress components will be 0. So take note of this. As you can see now, we can actually simplify our analysis to 2D rather than 3D. Yes? So let's try now to have some derivation. Now the first thing that I would like to derive will be your, the first thing that I need to derive will be equilibrium equation. Now, the equilibrium equation still, take note that we're still dealing with statics. We're still dealing with statics, it's not dynamics. So the principles of statics that you have studied are basically applicable to this, this work. So let's have a look at a 3D element. Of course, we know that you have your normal stresses, and then you have your shear stresses there. But what I'm going to do is just look into a 2D element. So that's your 2D element. And then say, for example, this is your axis 1, and then you have your axis 2. And then, let's put in the different stresses that are acting on this one. Let's just put in the, okay, let's just put in the stresses. So this one now is sigma 1, 1, that's your one normal stress. And then you have now here your this one is sigma 1, 2. And this one is sigma 2, 2. Oh, sorry, sigma 2, 1. And then you have this one to be sigma 2, 2. Right? So they are in the positive axis. Now here's the thing. before that, let me just put one here. Say, since this one is infinitesimal, let's say that we have this one to be, say, this side, infinitesimal. So the distance or the length of this one will be, say, delta x2. And this one will be delta x1, meaning they're really small. Okay, so they are small. Now the thing is, from here to here, there will be a change in stress. So we have now here, this is delta x1 and delta x2. Okay, so let me increase that. So the thing here is that if I move from here to this point here, there will be that change of stress. So initially my stress here will be a sigma 1,1. There will be another stress here. It's not just sigma 1,1, but there will be an additional term, because this one moves from this point to that point. So we're assuming that there will be some changes. And this one, there will be a change of stress with respect to the distance, and then you multiply it by that distance, delta x1. So here we go. This one now is sigma 1,1 minus the change in the stress, partial derivative sigma 1,1 with respect to x1. So this is a change. You have to multiply it by that distance to be able to determine the stress. So this one is stress with respect to x. So stress divided by a distance. So you multiply by that distance, delta x1. Now we have sigma 2,1 here. Now, if this one moves down, there will be a change in stress. And that will be sigma 1,2 minus the change in sigma 2,1 with respect to x2, multiply that with distance delta x2. Okay, so think of this one as the gradient change, or the change in stress as you move down. This one is also the change of stress as you move from this point to this point along x1. So this is the change of the stress from this point to that point, but you have to multiply it by this distance to be able to have a stress value. And this one here will be the change in stress sigma 2,1 with respect to x2, change as you go down. You multiply that by delta x2. Of course, if you want to, you can put in sigma 2,1 here, sigma 1,2 here, and then sigma 2,2 change. What happens here is, I'm just looking at the one direction at the moment. So that what happens here, if I'm just taking the summation of forces along direction 1, this is equal to 0. Now this one is a principle of statics. So at equilibrium condition, the summation of forces is equal to 0, summation of moments equal to 0. So we're just applying the principle of statics that we learned before. So we're going now to sum the forces. So sum the forces. Now this one is the stress. What will be your equation of a force? stress is equal to force all over the area, so that your force will be that stress multiplied by the area. But since it's only 1D or 2D, sorry, so we can simply analyze this one as stress multiplied by that distance, say A multiplied by, say, X, something like that, A dx or whatever. So assuming that area is equal to A multiplied by, or sorry, that will be B multiplied by X, so that will be, one side is B, so simply stress is sigma X. The reason, of course, we cannot complete area, we just have one side here. Right, summation of forces 1 equal to 0. So what do we have? So force to the right will be positive, to the left will be negative, not a problem, that's our assumption. So what do we have? So what do we have? So we have, say, let's try this one here. So this one is along x1, so sigma 1, 1 multiplied by the face it's acting on. So where is sigma 1, 1 acting on? Where is sigma 1, 1 acting on? Stress multiplied by the area. But you cannot have an area, you just have a distance, this one here. Right? So what will that be? Sigma 1, 1 multiplied by? Sigma 1, 1 multiplied by delta x2. Yes? Let's move into the other side of the equation. And then this one now is sigma 1, 1 minus partial sigma 1, 1 with respect to x1. That's multiplied by delta x1. This is now is to be multiplied by delta x2. Yes? So what about your shear stress? What about your shear stress? So what about this sigma 2, 1 here? Sigma 2, 1 multiplied by? It's a shear stress. Force multiplied by, force is equal to stress multiplied by the area. So you want to get the force. So you have a stress multiplied by that perpendicular area. But we don't have an area, we just have a side. Right. So you have sigma 2, 1 multiplied by delta x1. And then of course you have this one here, this term here. So it's the same, minus a sigma 1, 2, a partial sigma 2, 1 multiplied by delta x1. So this now is equal to 0. So we don't have any more forces acting along the one direction. So have a look. So it's just summing up the forces. It's probably some new terms. The reason we have delta is just saying that it's a small element or the size is really small. So what do we have here? We can cancel a few things here, yes? Now, sigma 1, 1 multiplied by delta x2 minus sigma 1, 1 delta x2, yes? So let's just put it here. So sigma 1, 1 delta x2 minus sigma 1, 1 delta x2, you can cancel that later. And then you have here partial sigma 1, 1 with respect to x1 delta x2. Sorry, delta x1 delta x2. Okay? And then we have another one here. Plus sigma 2, 1 delta x1 minus, this should be sigma 2, 1, yeah? Sorry for that, that should be sigma 2, 1. So that this one will be sigma 2, 1. Okay, sorry for that. So that we have now here sigma 2, 1 delta x1 plus partial sigma 2, 1 x2 delta x2. Yes? So you have it now, yeah? So this, of course, you can cancel this one out. And then you're left with this one here. So can we remove now here delta x1, delta x2? Since this one is 0 anyway, so we can remove now delta x1 and delta x2, yes? So just remove it there. So we end up with, what do we have? Partial sigma 1, 1 with respect to x1 plus partial sigma 2, 1 with respect to x2. This is equal to 0. Yes? Remember the comma sign? So we can write this one as sigma 1, 1, comma 1. Yeah? Meaning differentiation. Plus sigma 2, 1 with respect to 2, comma 2. Sigma 2, 1, comma 2. Now, let's try to write this one in initial notation form.
Sorry.
How do you write this one in initial notation form? So let's have a look at this one here. Partial sigma try to make it simple. Partial sigma ij. Yes? This one is partial x what? I or j? I. So how do you write this one now here? Sigma ij, comma I. So you can do the same. Take the summation of forces along x2, you'll definitely come up with the same thing. So this one is equal to 0. Equilibrium equation, because you're using the principle of equilibrium. So all the forces acting upon, say along one direction, acting upon that element is equal to 0. So you can do the same with the transverse axis or the longitudinal axis. You'll end up to have this equation here. So this is called the equilibrium equation. Questions, anyone? Now, let's move on with symmetry. Since we're here anyway, let's try to prove that sigma 2,1 is equal to sigma 1,2. Let's try to do that. The reason is, of course, once you know that sigma 2,1 is equal to what? Sigma 1,2, then of course the independent stresses will be, for a 3 by 3 matrix, will be 6 rather than 9. So let's try to rewrite this one here. Let me redraw it again. So we have this element, yes? And again, knowing that this element here, this one will be delta x. So that's 1 and 2, or x1, x2. So this one is delta x2, and this one will be delta x1. So that will be x1 or 1, and that is x2. Now, what are the stresses acting on this one again? So we have now here, say, sigma 1,1. And then we have another stress here. So again, we were able to identify this one as sigma 1,1 minus that partial derivative sigma 1,1 with respect to x1 delta x1. So you've done that already. And then we have here sigma 2,2, and this one will be the same. So if that is sigma 2,2, you will have here sigma 2,2 minus partial sigma 2,2 with respect to x2 delta x2. Right? What else do we have? What else do we have? We have the shear stress, sigma 2,1 or sigma 1,2. And then we have now here sigma 2,1. And then of course you have here that will be, I'm looking at this stress here, that will be sigma 2,1 minus the partial derivative sigma 2,1 with respect to x2, delta x2. And then of course you have now here so I'm looking at this stress here, sigma 1, 2 minus partial derivative sigma 1, 2 with respect to x1, delta x1. So as you can see, we're putting now sigma 1, 1, sigma 1, 2. Let me try to make this one clear. Sigma 1, 2. So we have sigma 1, 1, sigma 2, 2, sigma 1, 2, sigma 2, 1. And on the other side, we have sigma 1, 1 minus this small term here that mentions that there is a change of stress as you move from this point to that point. It's the same is true with this one here. Sigma 1, sigma 2, 2, you go down here, there is a sigma 2, 2. But this one also mentions that there's a small change of stress as you go on from this point to that point. So what do we do to solve for the symmetric condition? How do we prove that sigma ij or sigma 1, 2 is equal to sigma 2, 1? So still, we are considering statics here so that the principle of statics applies. So let's have a point here. Say 0. So that the summation of moments, right? What is the principle of statics? Summation of forces equal to 0. Summation of moments equal to 0. So let's apply that summation of moments equal to 0. So what will be our fulcrum? That will be point O. So let's take now that the summation of moments about O is equal to 0. What do we have? So let's see. Okay, let's have counter, or let's have clockwise to be positive and counter to be negative. So let's try to do this one here. Let's start with sigma 1, 1. Summation of moments about O is equal to 0. Let's start with sigma 1, 1. What is your moment about O? So you have to convert a force, right? Force multiplied by the perpendicular distance, yes? But what is our force? Stress multiplied by delta x2. And what is the perpendicular distance? That will be delta x2 divided by 2. So let's do that. What is the moment? Force multiplied by the distance. What is your force? Sigma 1, 1 multiplied by delta x2. What is your moment arm? This one is clockwise. So this one here. So this one is clockwise.
Plus.
Correct? Clockwise? Okay, good. At least we understand. So what is your moment arm? What's your moment arm? That will be this distance divided by 2. So it will be acting at the middle. So this distance divided by 2. So that's the moment arm. Delta x2 divided by 2. So are we ready now? So you have seen now the trend. So let's have a look at this one here. Sigma 1, 2 is counterclockwise. So sigma 1, 2 multiplied by the area it's acting upon, that is now delta x2, that is now your force, yeah? And what is your distance? Great, thank you. There we go. So it's just a drift now. We can now calculate for, or we can now just simply apply the summation of moment equals 0 rule. So we have now here, say for example, sigma 2, 1. Sigma 2, 1, and then it's acting on a phase delta x1. Yes? And what will be its moment arm? Delta x2. Positive, negative? Positive, right. So let's look at sigma 2, 2. Sigma 2, 2 is negative. Sigma 2, 2 is negative, and then applied sigma 2, 2 multiplied by delta x1. What is the moment arm? Delta x1 divided by 2. Yep. So where are we at the moment? This is okay, that's okay. So these two guys, since this one is distance is 0, so this one can be neglected since the distance, the moment arm is 0. Sorry for that. This one is, and this one can be neglected because the moment arms are 0, yes? So we can only consider this one and this one. Let's look at sigma 1, 1, this one here. So this one is minus sigma 1, 1, partial derivative 1, 1 with respect to x1, delta x1. So just treat this one as one term, one stress term. This is to be multiplied by delta x1. And what is the moment arm? Delta x2 divided by 2. So just take this one, don't be confused here. Just take this one as a single term. So delta x2, okay. Delta x2, and the moment arm is delta x2 over 2, okay? Thank you very much for that. So finally, let's look at this term here. It is clockwise, sigma 2, 2 minus partial sigma 2, 2 with respect to x2. Delta x2, again, treat this one as a single stress value. So this one will be acting along this phase here with the distance delta x1. And what will be the moment arm? Delta x1 divided by 2. So again, we need not consider these two guys here since the moment arm is equal to 0. So not a problem, they will also be 0. So this one now is equal to 0. Good. So it's easy to say that we have a symmetric condition, but the thing is, how do we prove that sigma 1, 1 is equal to sigma 2, 2 in the first place? So let's do that. So let's try to expand, shall we? So let's have a look at this one here. I'm looking at this one here and this term here. Yes? Just to cancel the things, sigma 1, 1 delta x2 all over 2 minus, so I'm just looking at this one multiplied by that. So this one now is sigma 1, 1, sigma 1, 1 delta x2 divided by 2. So you will see that they will cancel out. What else can we remove? So we we can take this one first. Minus sigma 2 delta x1 delta x1 divided by 2 plus sigma 2 delta x1 all over 2. So as you can see, they will cancel out. So let's try to look at the other terms now. So what are the other two terms? The other two terms are minus sigma 1 2 delta x1 delta x2. So let me just interchange these two guys. And then plus sigma 2 1 delta x1 delta x2. And then we have these other two terms here. So this already is up there, this is up there, so let's try to look at this term here. Plus partial sigma 1 1 with respect to x1, delta x1, delta x2, delta x2 divided by 2. There you go. And then this other term here, finally, sigma 2 x2 delta x2 delta x1 delta x1 divided by 2 equal to 0. Okay, this one is simple. 0, they cancel out, that's 0. Yes. Finally, we have this one here. We have a small value, as we are discussing earlier. We have a infinitesimal dimension. So we have a small value, multiply that with a small value, what do you have? 0. Very small. You have a very small number. But you multiply it with another small value, then you have a very, very small value. Right? Small multiplied by small is very small, multiplied by another small, very, very small. You can consider this one to be 0. So have a look, 1, 2, 3. Of course, 1, 2, don't consider that to be 0 at the moment. But you have this to be infinitesimal values. So maybe 0.01, 0.02 multiplied by another 0.01 and another 0.01, then you really have a neglect, you can neglect that value already. So you can consider this one to be zeros. So you end up now with sigma 1 2 delta x1 delta x2 equal to sigma 2 1 delta x1 delta x2. Cancel that one out. Sigma 1 2 equal to sigma 2 1. Sigma ij equal to sigma ji. So you can do the same with the other dimensions. So that is now your equation of symmetry. So the you have a symmetric stress. Sigma ij is equal to sigma gi. Sigma 1 2 equal to sigma 2 1. Sigma 1 3 equal to sigma 3 1. Sigma 2 3 equal to sigma 3 2. So let's have a break before we continue. 10 minutes.